Now I'm going to explain this without any equations, and I'm going to explain it without any maths. I'm going to do it all geometrically, simply, for a layman to understand, because that's what I am. And if I'm wrong, you tell me I'm wrong. The first thing that we need to understand is that a gyroscope is not a thing. The first thing that we need to understand is that gyroscope is a word, but it is not a thing. This isn't one thing. You've got to get that into your head. It's not a thing. And if you imagine you're standing there and you are hurling a ball around your head on a string, that's what you're being like a gyroscope then. Taking yourself out of it, then that's a gyroscope. If you then do that with another ball on the other end, and in fact if you had lots of arms, and you could do that with many balls all at the same time, and they were all the way around you, that is more akin to what a gyroscope is. So as you can see, it isn't one thing. Now these balls are all connected to each other in a rim, but in order to work out what's happening, we don't actually have to think of it as a ring. In fact, it's unhelpful to do so. It's better if we think of it as a series of points on tangents rotating. And I will make this reason why clear in a second. So for the purposes of this, we only have to analyse the forces that are acting upon one of these balls, and that will tell us what's happening to the entire ring, because all these balls are doing the same thing. So if we work out the forces that are being applied to any point on the tangent, it will tell us what is happening to the whole ring. Okay, if you've got that clear. And for this reason, when we talk about a gyroscope, we only need to talk in these two dimensions. There's a third dimension when we're doing technical drawing. We have our little house like this, okay, and we have our plan view. So we have our elevation, as I called it, the elevation. We have our plan, and then we would have another view here. That would be the house as we're looking at it from this side here. Or if you're American, from this side here. Doesn't make any difference, but it's just different in America. So if you're looking at the house and you look at it on this side of it, you'd have that elevation from there. And as you're looking at there, you're having that plan there. So in an English view, you're looking at it that way, and it shows you what you're looking at there. When you're looking at it that way, it shows it there. But because this is doing exactly the same thing this way and this way, that's to say, I'll do the gyroscope. Sorry, I've got ahead of myself here. Let's draw the gyroscope. Here's the gyroscope. There's the ring going round it. There's the spindle. When we look at it from this side, we still see the ring and the spindle. So it's exactly the same. So we don't need this elevation. When we look at it from this side, we get our plan view, which looks like that. Okay. So drawing of the gyroscope, if we're applying the rules of the house to it. Side elevation, or let's say front elevation. Side elevation, exactly the same, don't need it. We could do an unlimited number of elevations, you know, just as with the house. We could do a sort of half elevation like that. In the case of the gyroscope, it's always going to be the same, because they're all the same. The plan, though, we want to look at separately. That will be different. So the elevations, all the same. So what that means in effect is that there's only two dimensions to examine. We only need to look at the forces acting in two dimensions. Not three. So the gyroscope, when we look at it sitting there like this is a three-dimensional picture of it. In effect, we can take a slice that way, 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 and they're all going to be showing us this exact same thing, and we end up with something that looks a little bit like an oil filter. Okay, with all these fins. All these elevations will be exactly identical, and then the plan view, which is overhead, which I could do in a different colour I suppose, would be like that. And there's our gyroscope in the middle of it all. Got it? Good. Now, here we are with our Mexican cowboy, our gaucho, flinging these balls around his head. And there's a thing called centrifugal force. So we're going to go to the plan view to start with. Okay, we're going to go to the plan view, looking over the top, looking over the roof of the house, and looking over the top of the gyroscope. And I am going to use the word gyroscope, even though, as I say, it's not a single thing. Very important. Okay, so I also will point out later on something about the spindle, but not just yet. Here we are. All we need to analyse is this one ball. Now the centrifugal force, if you've ever stood in one of those big drums at the fun fair, and all the people stand inside it, and they all get crushed against the side, because they say the centrifugal force, and here's our plan view with all the people standing around the edge, centrifugal force is working like that. That's not true at all. That is not true. That's not what centrifugal force is. In fact, what's happening is that anything that is travelling always wants to continue travelling in a straight line. So any point on the tangent is going to be deviating from the wall of the circular drum that you're standing inside. So in effect, what you've got is a railway train. You are a railway train. You're being propelled along at speed, although you're being propelled along at speed like this, because remember all these cross sections are the same. You're being propelled along at speed like this, in this direction every time. This is your direction when at any chosen point on the tangent. Okay, it's always like this. And you see the wall is curving. So it's just the same as if you're taking a train down a tunnel and the tunnel is dead straight. Okay? And then you decide that you're going to curve the tunnel and make it go in a circle. And the train cannot steer, but it cannot stop either. What's going to happen? The train is going to hit the outside of the tunnel. It's going to keep hitting the outside of the tunnel all the way around. It's going to crash into the tunnel all the way around on the outside. Is that force being created like this? Is that what this force is? That's what they're telling you centrifugal force is. You're saying that the train, and this is going to be the plan view, as it goes around the tunnel and crashes and just constantly smacks into the side with its front right corner in this instance, and it can't stop, and it's bash, 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 bash. Are you telling me that that train is being pulled like that? Of course it isn't. It's travelling like this. It's travelling like this. It's trying to go in a straight line, but the tunnel curves round and it hits the side. Okay? So the force that's acting here is simply a force of momentum of the train wanting to continue in a straight line. That's all it is. The tunnel won't let it. It hits the sides. So getting back to this, with our gyroscope, what is the force that is keeping these balls on the end of their strings? this so-called centrifugal force. The force that's keeping these balls on the end of those strings is the fact that they want to travel in a straight line. But the string prevents them from travelling. If they were on a piece of elastic, then they would travel sort of like that, wouldn't they? They'd start to spiral out away from you. As you went round and round, they would start to move away from you. But because they are on a fixed length of string, they can't continue to travel like that, and as they go round you, you are actually in effect pulling them towards you. And the combination of this force pulling this way and you pulling this way, because if you let go of it, it's going to fly off, isn't it? It would just fly off like that. It would just fly away. So you are pulling, you are adding force here, holding it towards you. And it is adding force here to try and carry on in its straight line. And those two forces conspire to keep that string tight. Because in effect, this force here, of it trying to travel in a straight line, because of this angle here, it becomes a tiny force in that direction, in effect. But that is not how it is working. What it is doing is it's trying to go in a straight line. And anyone that talks about centrifugal force, they're going to talk about it being a tiny force in that direction. They're going to talk about it being a force in that direction. But it isn't. It really isn't. Then we're applying the force of this ball to this one here, and that's incorrect. What you're saying is that this ball, by the time it gets to here, when it's travelled from here to here, that by the time it gets to here, the differential creates a force. Well, differential is not a force. The differential between moment A and moment B is not itself a force. It's just taking two frames of a movie. There could be a number of reasons why it's in a different position, and I'm saying that the reason it's in a different position is because of the momentum in this direction, combined with the string holding it in place. And this is extremely important to understand. You will see why later. Now, that is the plan view. And it will tell us something about why the gyroscope stays up. And the reason that the gyroscope stays up is the same for the plan view and the elevation. But they are both working slightly differently. The elevation is the most exciting part, so let's just deal with the plan view. If we've got our gyroscope, which as I say doesn't really exist, and we've got balls on the end of string, this ball is trying to move, and let's say for the sake of argument it is moving in a straight line here. We've got the tangent here touching against it, but forget about that for a second, because if it's moving in a straight line here, and it's moving in a straight line here, and it's moving in a straight line here, all instances are identical all the time. So in that case we can actually forget about the circle, and we can actually just say that what we have is one ball here going that way and one ball here going that way, and we can say that whatever happens to this ball happens to this ball a split second later. Are you following so far? And whatever happens to this ball happens to this ball a split second later and to this one a split second later. So they're all doing the same thing. So we actually only need to analyse one and say that what it is doing will be equalised on the other side. Okay? Got that so far? Got that? So let's suppose that the gyroscope is trying to move, or we're trying to move the gyroscope in a certain way. Say it's balanced on my hand and I'm trying to move it around. Anything I do to it, any movement, will add a minuscule amount of momentum to this ball here. So it will speed it up. But a split second later, that ball's going to be here. It's It's going to speed up there as well. And it's also going to do it there and there. Any movement that I add to the gyroscope will be added in every direction a split second later. And it doesn't need to be instant. We're not talking about light speed here. We're talking about brute Newtonian physics, right? This thing is moving fast enough that the effects of gravity, which are very weak and quite slow on something that's balanced, will have time to be shared in every direction by its spinning. And the faster it is spinning, the quicker and the more generously this momentum can be shared out in every direction. Now let's go to the elevation. Let's do a new page. Here is the gyroscope balanced on the edge of a desk. One ball on a string and one ball on a string. Now, suppose the gyroscope starts to fall off the edge of the desk. What's going to happen? Well, this ball here is going to start to move downwards. But a split second later, that ball's going to be here, isn't it? So, think of it. This is one cross section, but think of the cross section. We'll take away the shaft for a second, and we're going to look at the one that's behind it or in front of it. Let's say that this is the one behind it, and it's travelling like this, behind the shaft, and here's the edge of the table. Because it's a tangent, because it's travelling on the tangent, we can analyse it as if it's just travelling in a straight line. Just for this tiny minuscule part here. We don't need to worry about the tangent because now we are on the elevation, and in fact the tangent of the circle and the direction, they're in this. When we look at, let me try and explain. Here we are looking at it almost in the elevation, and here is the thing, the ball travelling on. Do you see how they're started to line up? And by the time we're looking at it completely side on, in fact, the circle and a straight line are aligned. So we can analyse the ball in an elevation view. This is the elevation view. It's a side looking at the house face on, remember? We can analyse that as if it's travelling in a straight line. We don't need to worry about circles for this. We used circles for our plan view, looking at what's happening there. And that was in order to talk about centrifugal force, to explain what centrifugal force is, which I've done, which is really just a ball trying to travel in a straight line. Well, here we really can look at the ball as travelling in a straight line, because that really is in effect what it's doing at the tangent. And since, as we've already proved, the ball does the same thing at every single point, it's identical, we don't need to worry about the circular matter at all. We can actually just think now of the ball as a bullet travelling along. We can think of it as a bullet travelling along, but with a one difference. Okay, really good difference. So here's our bullet. We've fired a bullet from our gun, and it's travelling along. Bang. What does a bullet do as it travels along? It starts to fall. Yeah, the gravity starts to make the bullet fall. But if it's attached to the gyroscope, it's going to make the gyroscope fall over like that, isn't it? But the gyroscope takes it round and turns it round and brings it back. So whatever gravitational force has been added as momentum to the bullet, a split second later, the bullet is here, isn't it? So that momentum is going to be transferred to the other side of the gyroscope. And it's going to correct the falling of the gyroscope off the edge of the table. And this will happen with all the balls that we're throwing, all these different balls that we're flinging around our head, infinite number of them to make the ring of the gyroscope. All of them, it's doing to them all of them in all directions at once. And so that is the reason that the gyroscope does not fall over. And the faster it spins, the quicker it corrects. It's a self-correcting device. And the more the gravity tries to pull it over, the more, that's to say, the quicker it starts to fall, the quicker the gyroscope starts to topple over, the greater the amount of momentum on this bullet. And when it goes to the other side, it simply means that there'll be more to make it go straight again. So the gyroscope is going to constantly right itself and try and get to stand up. And it's because of gravity, not in spite of it, that the gyroscope stands up. It is gravity that makes the gyroscope stand up. Without gravity, the gyroscope would not stand up. Right? It would just spin on its own, and it would never change. It would spin like a space station, and it wouldn't change in any direction at any point. But as soon as you try and add gravity to any point of it, the gravity is transferred to the other side. Now, if you think of these balls as all doing the same thing, that you've now explained the entire ring around the gyroscope, the ring. You haven't explained the axis yet, the spindle. However, let's blow up the spindle. Make it really big. And let's hollow it out. And let's divide it into sections. Like that. And let's take slices of it. Because do you remember we said what happens to every ball is identical all the way around. What have we got here? If we then put an imaginary man in the middle of our spindle, and we give him a string and attach it to each of these little blocks, well, we've got the same thing again. And if we repeat it, so basically, if we have a man standing here with a string, and we take the string away, and we just add enough balls all the way around him, and then we keep doing that with another man standing on his, on each other's shoulders, then we could actually build an entire spindle out of the balls. So in fact, it doesn't, and the same goes for the axles. They're just longer strings with balls on the end. And there's how our axles are built. So there, like I say, there is no such thing as a gyroscope. Every single part of the gyroscope behaves as one of these balls, and they all have the exact same function of simply transferring the weight very quickly from one side of the gyroscope to the other. And that is why the gyroscope does not fall over. Now, what happens when we do it with the dumbbell, the barbell, and we hold the barbell? So we've got the barbell and we hold it like this, and it's a spinning, and it's very easy to lift because apparently all the weight has been transferred to the pivot point where you're holding it. Well, do you remember what we've just said about everything? Even the axis, everything behaves as one of those gaucho's balls being whirled around his head. Everything behaves as that. So this whole thing behaves as if you are simply hurling a ball on the end of the string around your hand. The whole thing behaves like that. And any action of gravity upon that ball, a split second later, is transferred to the other end. Any action of gravity on any ball here is transferred in the other direction a split second later. So the thing does in effect become weightless. But there is a differential between the amount here, because gravity is still acting on this force here. This is here is your momentum that the gravity has added. This is the bullet being fired, which would be towards us or away from us, because we're using the tangent at the very bottom of this spinning weight. So it's coming, say, towards my eye, right towards my eye here. And as the bullet drops, oh, I forgot I've lost my thread. This bullet is dropping, yes, so it's travelling in this direction. As it travels towards you, it's travelling and it's dropping. It's travelling towards you, and it's dropping. And so then when it's going this way, it's going up. But obviously a little bit of gravity, a small amount of gravity, is then added to that one. However, a split second later, that small amount of gravity gets added back to this ball. Do you see, this bullet? So that's the reason that the thing appears to be apparently weightless. When you cancel all these out, you will find that the weight at this point will be equivalent to if you had stood the thing up on its end like this and held it on the end of your fingers. Okay? It will feel then the same weight, and this weight will be equal to the weight here. Why is it equal? Because this is just a self-cancelling amount, isn't it? Always, it's self-cancelling. But what it is doing is it is effectively transferring all the weight onto where you are holding the string. You're effectively flinging this whole thing as a string around and around, and we can imagine this weight being anywhere. It doesn't matter. It's going around and around here, but because we fixed it in place with this spindle, it might as well be going around and around your hand. It doesn't make any difference, because these forces, these gross and these minor forces, they will all be working on the whole thing as a whole, because you've joined it all together. If this was a piece of string instead of a solid spindle on the barbell, you try doing the experiment, or like, even if it's a soft length of plastic, and you set it a spinning with your drill, and then hold it on the end of the soft length of plastic. You tell me then that this goes weightless. It won't. It will drop to the floor, because this length of plastic isn't rigid enough. So this length of plastic, this metal bar, because it's a set fixed tube, forces the whole thing to stay together, and that means that these forces that are happening where if we go back to the barbell and look at it as you would look along the man here looks along the tube. He looks along the tube and he sees the barbell like this. These forces that are all doing this, it doesn't matter where they're doing it along the length of that tube, because it's forcing them all onto the tube itself. Do you see? So it's creating these up-down forces that are created by gravity and momentum, and the transfer of gravity and momentum. So these up and down forces are transferred into the bar, because it's fixed. And so your hand, as you're holding the end of that bar, is going to do whatever those forces do. If I lifted this, if I grabbed this barbell and I lifted it in the air, it's going to lift your hand. So all these forces on the barbell act directly upon your hand. It doesn't matter how long the bar is. And that's my comment on the barbell situation. For the purposes of a gyroscope, it is exactly the same. Because we have fixed the gyroscope together as an assembly, spindle and what would you call this, the ring, but I like to think of it as a row of balls, because, as I say, a gyroscope isn't one thing. It's not one thing. And the reason I say it's not one thing is because when we look at a gyroscope and we see it as spinning, this bit of the gyroscope is here in a second, and this bit of the spindle is here in a second. And so the gyroscope, rather than thinking of it as a thing, think of it as a device for the transference of gravitational force. And think of it as a device for the self-cancelling transference of gravitational force. that's it. I hope you've enjoyed it. If you think I've broken any new ground, let me know. But I hope that is a sufficient layman's explanation of how a gyroscope is a self-righting device. Even if it's not a gyroscope, it's not a thing.